This is a 2003 past paper. It's a momentum and impulse question, and on any of these types of questions what I would normally do is draw a little diagram of what's happening before you do anything else. So you have two ice skaters that are stuck together, so you've got two objects, well not stuck together physically, but they are skating together. One of them has a mass, the guy has a mass of 54 kilograms. The lady skater has a mass of 38 kilograms, and they are both moving with a common velocity of 2.2 meters per second. This is before, it's not really a collision here, it's more of a separation. But the same rule of conservation of momentum applies. So then they move apart after that. So you would indicate that they are separate here. The woman moves off with a velocity of 4.6 meters per second. And the guy is moving off with a velocity that isn't known at this point. So that sets things out nicely. You don't actually need to use that diagram fully until part C, but it's good just to have that so you understand what's happening. So part A, calculate the magnitude of the change in momentum of skater S. So it's how much the momentum of the female skater has changed. So we know that change in momentum is equal to mv minus mu. So that's your initial momentum taken away from your final momentum. So the mass is 38 both times, the final speed is 4.6, the initial speed is 2.2, which gives you 174.8 minus 83.6, giving you a change in momentum of 91.2, and remember that's kilograms meters per second. So that's part A. Part B. How long does skater R exert the force on skater S? So anytime a time of impact or a time of force is mentioned, you know that you're going to have to calculate impulse, which is force times time, and impulse is equivalent to change in momentum, which you've already calculated. So impulse Ft is equal to change in momentum mv minus mu. You've already calculated what the change in momentum is. The force, the average force, is given in the question. It says an average force of 130 newtons. So it's 130 T being equal to 91.2. Time will come out as being 0.7 seconds. C is when you start to use your conservation of momentum equation. Calculate the velocity of the skater R immediately after pushing skater S. So it's this velocity up here that we're going to end up calculating. So in order to do that, we need to set the total momentum before equal to the total momentum after. So that will give you 54 times 2.2. I've done these separately here, but you could just add your masses together and multiply them by a common velocity. The end result would be the same. 38 times 2.2 is equal to 54 V1, because V1 is not known, plus 38 times 4.6. So you'll end up with 118.8 plus 83.6 will equal 54 V1 plus 174.8. If you bring this 174 across to this side of the equation, you'll end up with 54 V1 being equal to 27.6 and V1 is therefore 27.6 divided by 54, which will give you 0.5 meters per second. Now D, is this interaction between the skaters elastic or inelastic? So we'll do EK before first. Remember, an elastic collision is one in which momentum is conserved and kinetic energy is conserved as well. Momentum is always conserved in both of these types of collision, it's just whether kinetic energy is conserved or not. Inelastic means that EK is not conserved. In other words, it's not the same before as it is afterwards. So EK before would be equal to a half m1u1 squared plus a half m2u2 squared. So all you're doing is calculating the kinetic energy of each individual object there and then adding them together. So taking the kinetic energy before and then the kinetic energy after. I won't bother filling in the numbers there, but you'll end up with 130.68 plus 91.96. You'll get 222.64. So that's your EK before, and the EK after, we'll just scribble in down here. That's going to be a half m1v1 squared plus a half m2v2 squared. You'll get 6.75, that's a 6, plus 402.04, and you'll end up with 408.79. So that's your EK after. It's obviously more than your EK before. It's not simply enough to just do that calculation. You need to make some sort of statement at the end. It actually asks you, it doesn't ask you if the interaction is elastic or inelastic. It says, is it elastic? So I would say interaction is not elastic. There's more kinetic energy afterwards than there is before. Obviously that's because there's been some kind of push applied by that guy, so there's been more kinetic energy afterwards because of that force that has caused that kinetic energy.